Today we'll cover AS NZS 3500 Part 3 Stormwater Drainage. I will outline to you the key amendments to the previous version and the new updates, and their on-site implications for the design and installation. Please use this session as a technical orientation. You must consult the 2025 version in full and comply with other regulatory framework and manufacturer instructions for the design and installation. Since 2021, a few key things have changed in 2025 version. First, Clause 3.6 now increase the allowable catchment for valley gutters. Next, Clause 5.3.8 introduced new rules for how miscellaneous devices and appliances connect to the stormwater system. Importantly, Appendix F is now mandatory. It specifies EVA's gutter overflow requirements for roof catchment up to 400 square meters. Finally, there are editorial tidy-ups to make the standard easier to read, while the technical intent stays the same. Now let's dive into the detail. Clause 2.2.1 now includes Note 3. It requires plumbers to consider the quality and the quantity of stormwater discharge. This is to ensure it does not negatively impact council infrastructure or on-site systems, which means that you must consult the local council that has jurisdiction over the legal point of discharge and confirm that the quality and the quantity of your site discharge suit their network. If required, obtain consent from the relevant council. Clause 2.2.2 is a new addition to the 2025 standard. This clause requires that when we are selecting stormwater pipework, fittings, or products, we base our choice on two key factors: the anticipated discharge temperature and the quality of that discharge. In simple terms, this means you need to look what's being discharged into the stormwater system and how it might affect the materials used. The best way to do that is to get the discharge data from the manufacturer, things like temperature, composition, or any chemicals present. Once you have that information, you can then choose the right pipe material to suit those conditions. It's also a good idea to record the basis of your material selection in your documentation. That way, it is clear that you have considered the performance and compliance requirements of this new clause. Now let's look at Table 3.3.4, Annual Exceedance Probability, which has been updated to include EVA's gutter overflow measures. In Australia, EVA's gutter overflow must be designed for at least 1% annual exceedance probability AEP event. If you are wondering what exactly AEP means, according to the Australian Water Information Dictionary, annual exceedance probability is the probability that given rainfall total accumulated over a given duration will be exceeded in any 1 year. That doesn't mean the event only happens 1 in 100 years. It means there is 1 in 100 chance of it is happening in any single year. So the risk is always present, even if rare. You can find rainfall intensity for the suburb either in Appendix D, Rainfall Intensity for Australia, or directly from the Bureau of Meteorology website. And when we move to Appendix F in the next section, I will show you how exactly to use rainfall intensity values in a calculation example. Clause 3.5.3 is a new clause that sets the basis for designing overflow measures in EVA's gutter systems. When designing for overflow, start by assuming that all downpipes are fully blocked. Then, determine the catchment area in accordance with the method outlined in Section 3.3. Next, calculate the inflow rate Q*. That's the inflow volume in liters per second. Once you have established the inflow rate, move to Appendix F to select the appropriate overflow measure for your design. We will go through the detailed calculations steps when we cover Appendix F in more depth. Clause 3.5.3 requires you to include any upper roof that can discharge directly or overflow onto a lower roof. This ensures that if all downpipes are blocked, including on the upper roof, the overflow still works and prevents water getting back into the building. Of a higher 70 square meters of a roof area from an upper roof that can spill onto a lower roof of 80 square meters, you will need to design the lower EVA's gutter overflow for the combined catchment area, which is 150 square meters, not just the 80. In other words, always make sure your overflow design accounts for any additional roof area that drains down from above. Now there is a couple of scenarios where overflow measures are not actually required. The reason is simple. In these cases, any overflow water cannot make its way back into the building. It just flows clear to the outside, so there is no risk of water ingress. Here are two examples where overflow measures are not actually required. The first scenario is when Eva's gutter is fixed to a veranda or Eva's wider than 450 millimeters and there is no lining underneath. The second scenario is quite similar. It is a racked veranda or racked eave, again more than 450 millimeters wide, but in this case the lining slopes away from the building. In both of these situations, any overflow water has a clear path to discharge to the outside and cannot make its way back toward the building. So, no overflow measures are required. Now let's move to clause 3.6, valley gutters. The deemed to satisfy catchment limit has increased. A valley gutter may now serve up to 40 square meters. The limit was previously 20 square meters in 2021 edition. A new figure 3.6.2 has been introduced to assist practitioners in selecting the appropriate valley gutter widths based on the project's catchment area and rainfall intensity. Notably, the new figure now allows for catchment up to 40 square meters. To clarify, the term EW refers to the effective width of a valley gutter. It is the portion of the gutter that carries the flow of water below the freeboard level HF. The effective width is measured across the valley gutter and the design flow depth below the freeboard, and it varies depending on the gutter profile and the side angle. The table provided in standard table 3.6.2 was developed based on a freeboard HF of 15 mm. In 2025, figure 3.6.2 adds an alternative method to calculate the effective width of a valley gutter. In addition, an explanatory note to clause 3.6.2 permits CFD, computational fluid dynamics. CFD is a numerical simulation of fluid flow and heat transfer that use mathematical models to analyze fluids in motion. Accordingly, after you calculate the catchment area, choose the suitable method as follows. If the catchment area is 20 square meters or less, use table 3.6.2, or alternatively, you may use figure 3.6.2. If the catchment area is more than 20 and up to 40 square meters, you must use figure 3.6.2 only, not the table. Now, important note. The new figure 3.6.2 is under review by Standards Australia and should not be used in its current form. We will update you once a confirmed version is released. Now let's move into section 5, surface drainage. In this section, a new clause 5.3.8.1 has been introduced. It specifies the requirement to how to connect miscellaneous devices and appliances to the stormwater drainage system. This clause introduced two new notes. It is important to verify that the internal components can tolerate the discharge and confirm with the council that its quality, quantity, and temperature are acceptable. And if the council requires it, make sure to get their approval or consent before connecting to the stormwater network. Now let's delve into the detail. These clauses say that if a device or appliance discharges into the stormwater system, that discharge must occur through a tundish or a pit. In simple terms, no direct connection straight into the stormwater line. Now, Part B goes a step further. It requires that the discharge point be positioned so that steam or heated water doesn't cause nuisance and is easily visible and does not damage the building or harm anyone nearby. So in short, always discharge via a tundish or a pit and make sure the outlet is visible and safe. Now, still under clause 5.3.8.2 stormwater connection. These parts focus on what's required when you connect a discharge from an appliance to a tundish or stormwater pit. The standard now gives us 4 clear technical requirements to comply with. First, it must be accessible. Second, it must be securely fixed. When the appliance discharges, there should be no vibration or movement that could damage the pipework or cause water to splash out of the tundish. Third, it must allow the discharge to be visible. That means you should be able to see when water is being released. So if something discharges unexpectedly, it can be noticed early before it becomes a problem. Finally, a 25 mm air gap is required between the point of discharge and the tundish or the pit. That air gap protects against backflow and contamination. So, overall, this clause is really about safety and maintainability. Now we come to the last part of clause 5.3.8. The new clause 5.3.8.3, stormwater system design. It requires the stormwater system to be sized for the maximum discharge. So when selecting the pipe size, you are designing for the peak flow, not the average. There are 3 supporting notes, each linking back to earlier clauses. Note 1 directs you to the manufacturer's specification for discharge details such as flow rate, temperature, and quality. Note 2 refers back to clause 2.2.2, reminding us the material must be suitable for discharge condition and comply with the standard. Note 3 highlights the need to consider discharge quality and confirm whether local authority approval is required before connecting to the stormwater network. Now let's move to Appendix F, overflow design for EVA's gutters. This appendix has undergone a significant change in 2025 edition. In the 2021 versions, Appendix F was informative, meaning it was optional guidance. But in 2025, Appendix F is now normative, which means it's mandatory for deemed to satisfy solutions. Appendix F sets out the requirement for designing EVA's gutter overflow systems for roof catchment up to 400 square meters. The 400 square meters limit applies universally to all building types, both residential and commercial. There is no limitation in the standard that restricts this to small buildings only. Now, a few key clarifications based on our regulatory position. If the roof catchment area exceeds 400 square meters, a performance solution is required because this goes beyond the design parameters of the standard. However, to comply with the standard, a plumber can divide the roof into separate EVA's gutter systems, provided each system serves a distinct catchment area not exceeding 400 square meters. And the systems are generally independent, not just artificially divided on paper. Now let's look at clause F.2 overflow volume, which explains how to calculate the design overflow volume Q** that must be managed by EVA's overflow measures. You can find this value by multiplying the catchment area A by the rainfall intensity R and then dividing by 3,600. So the first step is to determine the catchment area A, that's the total roof area draining to EVA's gutters. Once you know your catchment area, step 2 is to find design rainfall intensity R, that's the 1% annual exceedance probability AAP for your project location in Australia. After you have got both values, A and R, you simply plug them into the formula shown on the screen. Q equal A multiplied by R divided by 3,600. Now, to understand why we divide by 3,600, rainfall intensity is given in millimeters per hour. The overflow volume is expressed in liters per second. So dividing by 3,600 converts hours into seconds. That's how you get the correct flow rate your overflow system must handle safely. So to summarize simply, A is your roof catchment area, the part collecting rain. R is the rainfall intensity, how hard it rains during the design storm. Dividing by 3,600 converts it to liters per second, giving you the overflow rate Q** that your EVA's gutter overflow system must discharge to prevent flooding or backflow into the building. Before we move into a detailed example, a quick but important reminder. If you are using rainfall intensity data from Bureau of Meteorology website, be careful because the Bureau of Meteorology website provides 2 different units. Millimeters per hour, this is the rainfall intensity, and millimeters. This is the total rainfall depth. For the purpose of calculating rainfall intensity R, in the overflow formula, you must use the millimeter per hour value. As you can see on the screen, the Bureau of Meteorology table includes a drop-down menu for the units. Make sure it is to millimeter per hour, not millimeter. If you accidentally choose millimeter, you will be using rainfall depths instead of intensity, and that will give you incorrect overflow results. So always double check that your data in millimeters per hour before entering into the formula. Now let's see how you actually find it. On the Bureau of Meteorology website, rainfall intensities or RFIs are shown in table like this. To find the correct value, go to the 1% AAB column because that's what the standard requires. Then look across to the 5 minutes duration row. Where the two intersect, that's the rainfall intensity value. In this example, the rainfall intensity is 218 mm per hour, and that is the correct figure to use in your overflow calculation. Now let's do a quick calculation example. Now using standard tables for the RFIs instead of the Bureau of Meteorology website. Let's say we are designing a roof drainage system for a house in Mildura and the roof catchment area is 200 square meters. We already know the catchment area, so the only thing missing is the rainfall intensity. Looking at Appendix D in the standard, we can see that for Mildura at 1% AEP gives a rainfall intensity of 219 millimeters per hour. That's the value we will use for R in our overflow calculation. Now that we have all the values, let's plug them into the formula in Appendix F.2. We have rainfall intensity R 219 millimeters per hour, catchment area AC 200 square meters, using the formula Q asterisk equal to area of catchment times rainfall intensity divided by 3,600. We substitute the numbers and Q asterisk will be equal to 12.17 liters per second. So the design overflow volume for this catchment is 12.17 liters per second. That means Eva's gutter overflow measures, whichever method you choose, must be capable of safely discharge, let's say 13 liters per second of stormwater, assuming all downpipes are blocked. Under F.2, Note 2 is important to highlight. The standard clearly states that the overflow design method does not account for the effects of debris buildup or the presence of snow, hail, or ice. This means that even if your design works perfectly under normal rainfall, its performance can be significantly reduced if debris, snow, or ice obstructs the flow path. Now, while you cannot always predict when this might happen, you can assess the likelihood based on the site conditions. For example, whether the property is near trees, vegetation, or planters that might shed leaves or debris into the gutters. In such cases, designers should take a conservative approach. Overflow measures that discharge toward the external edge of the gutters are generally a better choice, as they are less likely to cause overflow back toward the building. And for regions that experience snow, hail, or frost, additional design consideration should be included to make sure the overflow path remains clear and functional under those conditions. At the previous step, we have calculated the design overflow volume Q asterisk, which represents the amount of water that your overflow system needs to handle. Now, under clause F.3, overflow design, we move to the next step. This clause tells us that the overflow measure you select, whether back gap, slotted gutter, or front bead, must be selected so their capacity Q is equal to or greater than the calculated overflow volume Q asterisk. In simple terms, the selected overflow system must always be able to handle at least as much water as the calculated flow. Now let's move into clause F.4.1 continuous overflow measure and look at the general requirement for designing any overflow system. First, overflow measure must be continuous. This means the overflow runs along the length of the gutter rather than being located at a single point. The key advantage of continuous overflow is that if one section of the gutter gets blocked, the remaining length can still provide overflow capacity, so it gives you a level of built-in redundancy. Clause F.4.1 also tells us that the overflow capacity is given per meter per length. So, to find the total capacity Q for selected overflow measure, you will need to multiply the per meter flow rate by the total length of EVA's gutter serving the catchment. If you selected a back gap gutter that can discharge 1 liter per second per meter, and your gutter is 15 meters long, you simply multiply 1 liter per second per meter by 15 meter, which means that the gutter can disperse 15 liters per second in total. This is a simple but very important step because it allows you to check whether your selected gutter can actually handle the overflow volume you calculated earlier. Another general requirement to note here, regardless of which overflow measure you select, is the need for a freeboard margin above the maximum head of water in the gutter. This margin is important because it provides a small safety buffer to allow for things like construction tolerance, building settlement that could affect the slope turbulence in the water flow or even wind effects. The standards specify that you must have a minimum 3 mm margin for EVA's gutter with a slope greater than 1:500 and a minimum 6 mm margin if the gutter slope is less than 1:500. So for example, if you have designed your back gap gutter for a 10 mm head of water and slope is less than 1:500, then you will need to add that 6 mm freeboard margin, meaning the back of the gutter should sit 16 mm below the fascia. This ensures the system has enough allowance for any minor issues while maintaining proper overflow performance. We will talk more about the required head for each overflow measures in the following slides. Now, let's start with the first overflow measure for EVA's gutter in the new revision of the standard, the gutter back gap overflow. The gutter back gap is the small gap intentionally left and continuously maintained between the gutter and the fascia. It is important to ensure this gap is maintained along the gutter. This may be achieved by using spacers or any other method recommended by the gutter manufacturer. This gap acts as an overflow path when the primary outlet is blocked, allowing water to discharge safely instead of flowing back into the roof space or building structure. Table F.1 helps to determine how much water a back gap can discharge if the primary outlet becomes blocked. The discharge rate depends on the head of water above the back of the gutter. The higher the head, the greater the discharge capacity through the same gap. For example, if the average bottom gap is 6 mm and the head of the water is 8 mm, the back gap can discharge approximately 1.8 liter per second per meter. If the head of water increases to 12 mm, the discharge increases to around 2.6 liter per second per meter. Now let's look to the second overflow measure of EVA's gutters, slotted gutters. Slotted gutters have a small horizontal slots along the front edge, which act as a continuous overflow path when the main outlet is blocked. The standard gives us this formula to calculate the flow rate through the slots. It depends on two things: the total slot area A and the head of the water above the slots H. In practice, you don't need to calculate slot area manually. The manufacturer usually provides you the slot area per meter. Then, you will need the head of the water above the slot. That head should be selected to allow full discharge of the overflow before the water level rises high enough to flow back toward the building. So, in short, the design intent here is to ensure that when the primary outlet blocks, the slots safely release water outward, not inward. Now let's look into the third overflow method, the front bead overflow. The concept here is to position the front bead of the gutter at least 10 mm below the top of the fascia. By doing this, any overflow will naturally discharge over the front edge rather than the back toward the building. The standard gives this method a fixed overflow capacity of 1.5 liters per second per meter of gutter length. So if you multiply 1.5 by the gutter length, you will get the overflow capacity Q. Using this method, a 10 meters EVA's gutter can discharge 15 liters per second. However, it's important to note this method can only be used if the required overflow capacity is 1.5 liters per second per meter or less. If the calculated requirement is higher, or the 10 mm low front cannot be achieved, you must use another overflow method, such as slotted gutter or back gap overflow. The last option is designed by computational methods, such as Computational Fluid Dynamics (CFD). This approach uses advanced modeling to simulate how water flows and behaves under real conditions. It's intended for use only by qualified engineers or expert hydraulic designers with expertise in fluid dynamics and numerical modeling. CFD can support complex or non-standard gutter designs, but results must still meet all standard performance criteria. And that concludes our session today for the updates of AS NZS 3500 Part 3 Stormwater Drainage. If you have any further questions or require further information, you can contact us via email plumbingtechnicaladvice@bpc.vec.gov.au.